So good day. Today we will talk about chapter 2, operational amplifiers, capacitors and inductors for the FET 101 basic electrical technology. In this course we will talk about the operational amplifier. We have a short form we call as op-amp, and then we have an ideal op-amp, inverting amplifier, non-inverting amplifier, summing amplifier, difference amplifier, capacitors, series and parallel capacitors, inductors, series and parallel inductors. So what is op-amp? Op-amp is actually the operational amplifier. In short, we call it as op-amp. This is the symbols. We have a positive input, we have a negative input, positive supply, voltage supply, negative voltage supply. We have a non-inverting with a plus signal, inverting with a negative signal, and an output. Op-amp is a circuit of components that integrated into a one chip. This is one chip. We have a DIP package, SMT package, SMT package like this. This is the typical packages of the op-amp. And then will be used? It is used to model the basic mathematical operation in electronic and analog computers. For example, addition, subtraction, integration, differentiation. There are two DC supply. We have a positive DC supply and negative DC supply, one output terminal and two input terminal. Positive we call as non-inverting, negative we call as inverting. Yes. So the op-amp formulation, we have a V1 as an input voltage, V2 as input voltage 2, then we have an output voltage V0, and then inside we have a Ri, we have a minus plus Vd, we have R0, AVD. A stands for the open loop gain. Open loop gain A, please bear in mind, A equals to V out divided by V in. V out divided by V in, where V in is actually the V difference. V out divided by V in. This is the V in. Then V out, I will just copy V out. V difference is plus V2 minus V1. Plus V2 minus V1. So in short, for an op-amp formulation, V0 equals to A times V difference. V0 equals to A times V difference. Then we can put as A times V2 minus V1. Then A is our open loop gain. So no matter what type of the op-amp, what type of the application, we must remember A equals to V out over V in, or A equals to V0 over Vd. General application of op-amp. So what we are using? One of it, amplitude change. Input is like this. When it's passing through the op-amp, the signal has been amplified, or the amplitude has been amplified. We can change the polarity from positive, negative, positive, become negative, positive, negative. We also can use the op-amp as a comparator. So V reference, this is the reference voltage from the input V reference. This is the V reference, V input, V input. So whenever the V reference is lower than the V input, the V output will become positive. This is one of the comparator. Or whenever the V reference is bigger than the V in, it may be negative or zero. It depends on how we connect the circuit. We also can use as a filter circuit. For example, we have an input of a square wave input signal, and then if let's say we filter it, saying that only the low frequency can passing through. So this is only the low frequency can passing through. If only the medium frequency can passing through, this is the output waveform at the V out. If only have a high frequency can passing through, then this will be the expected V out. Or we can do it as oscillator. We put at a capacitor and connect few resistor, then it become oscillate. We have a positive plane, negative plane, positive plane, negative plane, it oscillate. Then it can be used in an instrumental circuit, where we use, for example, op-amp as a buffer. We use op-amp buffer and then we do it as a differential op amp connected together, and all over the modules. For example, this is one module, two module, three modules. All the modules are connected together. It becomes instrumentation circuits. So we will not go to the non-ideal op amp throughout the subject. We only focus on ideal op amp. So for the ideal op amp, what we have here is a negative. First of all, it must be infinite open loop gain, where the A must be go to infinity. This is the first assumption. Second assumption, it must be infinite input resistance. So the R input E across this one will be infinity until there's no current can go into the amplifier. And then zero output resistance. This one will be zero output resistance. No voltage drop inside here. This is the three conditions. So an ideal op amp is an amplifier. We amplify something with an infinite open loop gain, infinite input resistance, and zero output resistance. This is an ideal op amp for itself. We still not yet consider the outside connection. Okay, when there's outside connection, other circuit elementaries connected, then it becomes different gain. So when we have three types of assumptions, our I1 should be 0 because there's no current go in, and I2 will be 0 as well. And then we know that our V difference is V2 positive. The positive side is V2, negative side is V1. So V2 minus V1 must be 0. So when we talk about ideal op amp, the voltage at this node, and this node, it must be the same. So V1 and V2 must be equal. Okay, so I repeat, when we talk about op amp itself, this one, operation amplifier, is an ideal op amp. We need to have the so-called assumption. And then we need to know that I1 equals to 0, I2 equals to 0, then V1 equals to V2. These three things. One is a condition, one is the equation. So when we compare between the ideal and the practical op amp, so ideal op amp, the first condition, the input resistance or impedance must be infinite, and then for the ideal op amp, it has some resistance. Then the open loop gain will be infinity, but this one we have some open loop gain. This one is the practical one. Then the Z out will be 0, but we have a voltage drop in a Z out. Why we have a voltage drop? Is it because when there's a current flowing through this line, I times R, it becomes a V. So we will have a voltage here. So example, let's go through an easy example. Given V1 is a 2 volt, V2 is a 5 volt. So the open loop gain is 100, for example. Then find V out. So V out equals to A times V2 minus V1. So my A will be 100, 5 minus 2. So I substitute V2 here. V2 is 5, V1 is 2. Then I have a 300 volt. Which means if let's say my input V in is 2 volt, my output is a 5 volt, the difference is 3 volt. And then this difference will have a gain passing through the op amp. It becomes 300 from the output. But this is a simple equation. For the ideal op amp, it must be infinite. This one, A must be infinite. Okay, now we will look into the application of the op amp. This is an inverting amplifier. So when we talk about inverting amplifier, we need to know how the circuit connection. First, the positive side will be connected to the ground, which is 0. And then we will connect a resistor and a V input to the ground as well. Then from here, we connect a feedback resistor to the output side. If you still remember the assumption from an ideal op amp, it will be 0 ampere go inside, 0 ampere go inside for this ideal op amp. So which means all the I1, I assume that I1 flow into here, it will directly go to I2 here. I1 will flow in and then go to I2. Since there's no current flow into the ideal op amp. So I equate it become I1 equals to I2. Then how can I find my I1? So I use a higher voltage here, which is Vi minus V1, because the current is flowing from high potential to low potential. So high potential is Vi minus low potential to V1. So divide by R1. This is my equation. And then from high potential flow to low potential. So my V1 minus V out divided by RF, it is my I2. So for an ideal op-amp, V1 must equal to V2. So V1 here must be equal to V2. And I know that my V2 is 0. So my V1 will be 0 as well. So V1 0, 0, and then I and I got it, become V1 divided by R1 equals to negative V out divided by F. Then I again, I have my V out equals to negative RF divided by R1 times V in. Remember this one. This is the most important. We call it as an inverting amplifier because A is negative. The gain is negative. If you still remember, we are saying that for an op-amp, the gain will be infinite, means infinity. So, but when we do some connection with the passive element resistor, then we found that not passive element. We connect with the resistor, then we found that actually we can get some gain using this equation. So an inverting amplifier reverses the polarity of the input signal when amplifying the signal. So for example, if my Vi is positive, when I passing through this amplifier, my Vout will be in negative value because the gain here will be negative. Then we call here this one as a feedback resistor. For example, for an inverting amplifier, if my Vi equals to 0.5 volt, and then my R here 10 kilo ohm, my feedback as 25 kilo ohm, we need to calculate the output voltage V out and the current in the 10 kilo ohm resistor. So first of all, I use back the equation that we have derived, which is this one. Okay, then V out divided by Vi equals to negative RF divided by R1. So I substitute 25k here, 10k here, and know that this is negative 2.5. Where I know that this is called gain because I use my output divide my input. So I use back the previous equation as well. V out equals to A times V in. My A is negative 2.5. My V in is 0.5. Then I get my value of negative 1.25 volt. How to measure the current? So I know that the current is from higher potential flow to lower potential. Then my higher potential is Vi, my lower potential will be 0 because my ideal op-amp assumption is V1 here must be equals to V2 here. So my V2 is 0, so this one will be 0. So Vi minus 0 divided by 10 kilo ohm, then I have my 50 microampere in this section. Just now we talked about the inverting amplifier. Now we talk about non-inverting amplifier. First of all, we need to see the circuit. So non-inverting amplifier, we have an input voltage at the V2 side. And then we also connect the feedback resistor between V1 and V out. And then we connect from a resistor R1 from V1 to the ground. So this is called non-inverting amplifier. So for same as well, I need to find some feeling of creating the equation. So I assume I1 is flowing from here, I2 will flowing to here. So I1 is actually equals to I2. Since an ideal op-amp, there's no current flowing through into negative terminal or positive terminal. So I1 equals to I2. So higher voltage minus lower voltage divided by R. So this is 0 because higher voltage here is 0. 0 minus V1 that I don't know, divided by R1, which is my I1. So my I2 is higher voltage minus lower voltage. Higher voltage is V1, lower voltage is V0, so that the current can flow from V1 to V0, divided by my feedback resistor. Then we know that for ideal op-amp, V1 equals to V2. And now in this case, my V1 is actually VI. So I substitute my V1 with VI, V1 with VI, then I play some magic. Then I found that V0 equals to 1 plus RF divided by R1 times Vin. So a non-inverting amplifier is an op-amp circuit that is designed to provide a positive voltage gain. So we can see that 1 plus RF, Ri, R1, it is a positive gain. We call it as a non-inverting amplifier. So further detail, if RF is 0, R1 is infinity, then A1 will be 1. Okay, for example, we apply this equation, RF is 0. 0 divided by something, everything will be 0. 1 plus 0 is 1. So when it is 1 means it is A equals to 1. So the circuit will become like this. We directly connect my output to input. Then the equation will transform from here to V out equals to VI. We call this one as a voltage follower. What input we input here, we will get the same output as the input. We call voltage follower, or we call as a unity gain amplifier. Unity gain means A equals to 1. Or buffer amplifier. Buffer means we want to delay the signal. Or for example, the signal from here to the output, it took some time of 1 millisecond, for example. So it will be buffered. Buffered means we delay. The output follows the input, yes, and then we use as an intermediate stage amplifier to isolate one circuit from another. Isolate the circuit. For example, we feel that the circuit from my right hand side will influence the circuit from my left hand side if I directly connect together. Which means, if let's say I have a 2 circuit and I connect together, sometimes it will short circuit. Then this will get burned. So how to protect the other side of the circuit? I need to get an isolator. Which means, if let's say here on my right hand side it is short circuit, then left hand side no harm, no damage. That's why we call it as an intermediate stage amplifier to isolate one circuit from another. So for example, for a non-inverting amplifier, when we talk about non-inverting amplifier, first we need to see the circuit. Second, now the RF is a 10 kilo ohm, R1 is a 4 kilo ohm, I have a VI equals to 4 volt, 5 V out. So I use back the equation that we have derived, which is V out equals to 1 plus RF divided by R1 times the V in. So 1 plus RF is a 10 kilo ohm. Then R1 is a 4 kilo ohm times a V in as a 4 volt. So my V out will be 14 volt. For in this case, with the arrangement of the R1 and RF, my V in when input as a 4 volt, I will get 14 volt output. Another one is a summing amplifier. So for example, in this case. So first of all, we'll go to the circuit first. So I have a voltage 1 with the R1 connected to the negative terminal. I have a voltage 2 with the R2 connected to a negative amplifier. I have a V3 with the R3 connected to negative amplifier. Then I have a feedback resistor across the negative amplifier, negative terminal and output terminal. Then I ground. I make the positive terminal become 0. So now I want to find some filling to create some equation. So I know that when the amplifier itself, it is an ideal amplifier. No current will flow through the negative terminal. No current will flow through to the positive terminal. So all the current flowing inside here will flow to feedback resistor and go to the output. So now I have my I here, which is equal to I1 plus I2 plus I3. Then what is my I? My I here is my VA minus Vout divided by RF. So I here will be the same as I here. So if I want to find the I here, higher potential to lower potential. Higher potential is VA, lower potential is Vout. So I use VA minus Vout divided by RF. So I have my I. What about my I1? I1, higher potential, lower potential. Higher potential is V1, lower potential is VA. V1 minus VA, V1 minus VA divided by R1. Same as well, I2, higher potential, lower potential. Higher potential V2 minus lower potential VA divided by R2. Same, V3 minus VA divided by R3. So for an ideal op-amp VA, it must be equal to V positive, where my V positive will be 0 in this case. So my VA will be 0. So VA 0 here, 0 here, 0 here, 0 here. When we put all together, then we found that my Vout equals to negative RF divided by R1 V1 plus RF divided by R2 V2 plus RF divided by R3 times V3. So this is called summing amplifier. We sum all the voltage together, then we get an output. So a summing amplifier is an op-amp circuit that combines several inputs and produces an output. That is the weighted sum of the inputs. For the application here, for example, I have a mic number 1 and I have a mic number 2 and I have a mic number 3, then the output will be the speaker. This is called summing amplifier. Example of the summing amplifier. Yeah, for example, I use back the equation Vout equals to negative. So now I have a 2 volt here. I use 10k divided by 5k, then I times 2. Plus I use 10k divided by 2.5k, I times 1. Then I have negative 8 volt here. Another example, find the output voltage of the following summing amplifier circuit. So, yeah, we use an equation, the same, same. Negative RF divided by R1, or RF divided by R1 times the voltage here. RF divided by R2 times the voltage here. So, negative 10 kilo ohm divided by 1 kilo ohm, then times 2 millivolt, plus 10 kilo ohm divided by 2 kilo ohm, I times 5 millivolt equals to negative 45 millivolt. Same as well, negative RF divided by R1 times V1, this one divided by this one times V1, plus this one divided by this one times this one, plus this one times this one, divided by this one times this one, then in negative, times with negative. So we found that if my V in is plus 3, my V in 2 is plus 1, my V in 3 is plus 8, my V out is actually negative 12 volt. So another one is a difference amplifier. The last one, difference amplifier. Let's have a look on the circuit as well. So we have ideal op-amp. Then we assume the current going into the negative and positive terminal will be 0. But this time I need to connect an R1 with the voltage here, R2 feedback, then R3 with the voltage here, R4 to the ground. This is called difference amplifier. For an ideal op-amp, I input negative is equals to I input positive, which is 0. So consider the I input negative as a 0 ampere at the node A, this one. So my I flowing through here will be equal to I flowing through here. So from I flowing through here, higher voltage minus lower voltage, V1 minus VA divided by R1. Okay? Higher voltage go to lower voltage, VA minus Vout divided by R2. So this is the current flow. Then we found that Vout equals to like this. Consider I input positive equals to 0 as well. at the node B. Okay, so which means my current flow here will be equal to current flow to here. So high voltage, low voltage, V2 minus VB divided by R3 equals to VB minus 0. Higher voltage, lower voltage, then VB minus 0 divided by R4. So we have another equation. Then we found this one. After that, for an ideal op-amp, VA must be equal to VB. In this case, we substitute and then we do some substitution. Then we found this equation. So since a difference amplifier must reject a signal common to the two inputs, the special of this amplifier is when the input here are the same, it must be rejected. So the amplifier must have the property that V out will be 0 if the VA and VB are the same. This is the properties. So if in this case only R1 divided by R2 is equal to R3 divided by R4. In this situation, the VA and VB will be the same. At the same time, V out will be 0. So when we have this equation, we substitute inside here, we have this equation. This is a little bit advanced, so a little bit confusing. So we will not go in depth, but just to let you know. Then a different amplifier actually is a device that amplifies the difference between the two inputs, but it rejects any signal common to the two inputs. Next, we will talk about the capacitors. So a passive element designed to store the energy in each electrical field we call as a capacitor. What is a capacitor? Capacitor actually is a two piece of the thing connected together with a voltage. For example, I have a two piece of paper, one paper at the top side, one paper at the bottom side. I connect the wire to the battery, then this will become my capacitor. When we call it a passive element, it will store the energy as electrical field. So it is a conducting plate, each with the area of A, dielectric with a permeability of E. It consists of two conducting plates separated by an insulator. So when there's a conducting plate together and then inside as insulator, then it becomes a capacitor. So what we use capacitor? Plates may in many applications, plates may be in aluminum foil, dielectric may be air, which means I have a plate, another plate, then this is air. Then I connect to a battery. Then this will become a capacitor because it stores the charge in as an electrical field. Dielectric may be air, ceramic, paper, or mica. So the source deposits a positive charge here on one plate, and then a negative charge here on another plate. When the voltage source supply is connected to capacitor. So when the voltage connected to the capacitor, positive will give us positive charge, negative will give negative charge here. So we need to put into a mathematics again. So the amount of the charge stored in the capacitor Q is directly proportional to the applied voltage V. So the total charge is actually to see how good the capacitance and then what is the voltage we apply. So C is the capacitance of the capacitor. It used to describe what is the capacitor value, capacitor parameters. The unit are in farad. So capacitance C is the ratio of the charge on a plate of a capacitor to the voltage difference V, which means the total charge on this plate, divided by the total voltage that we supply. This is how good the capacitor can store the energy, and then we call it as a capacitance, and it is measured in farad. So 1 farad actually is equal to 1 coulomb per volt, when epsilon is the permeability of the dielectric material between the plates. Another one is because capacitor is built by physical things, so we need to determine the capacitance value which is related to the material itself and also to the material itself, to the dimension. So another equation is used to describe in a geometry wise and a material wise. So we have a capacitance value equals to the permeability of the dielectric material. Permeability of dielectric material means the the properties of the material that we use in the capacitor. How good is that? If it is good, then capacitance will be higher. Then how big the area we have, and also how close. The closer we have, the higher the capacitance. The bigger the area we have, the higher the capacitance. The better the permeability of the material we have, the higher the capacitance. So A is the surface area of each plate, D is the distance between the plate. A is the pink color side, D will be different here. We can put the unit in a farad, picofarad, which is a 10 to the power minus 12. We can put in a nanofarad, 10 to the power minus 9. We have a microfarad, 10 to the power minus 6. And then three factors that determine the value of the capacitance. One, as we discussed before, the surface area of the plate. Another one, the spacing between the capacitor. And then the permeability, which is, we put it in this equation. So if let's say we want to have a higher capacitance, we may change either higher area or smaller distance, or we use better material. Okay, the symbol. We have a fixed capacitor. We also have a variable capacitor. Fixed capacitor plus minus V, then a variable capacitor with a arrow here. So this is a fixed capacitor. We have a polyester capacitor, the material is made by the polyester. We have a ceramic capacitor, the material of the capacitor is made by ceramic. We have electrolytic capacitor, which is widely used in industry. Firm trim capacitor. When we talk about variable capacitor, trimmer capacitor is the variable one. We can vary it. So if I is flowing into the positive terminal of capacitor, we call it as a charging. I is positive. When I is negative, it is discharging. So capacitor actually act like a battery. So another one, when we summarize, the Q is equal to CV. When we differentiate both sides with the time, so dq divided by dt equals to, C is a constant, we cannot differentiate. So differentiate V with the time, dv dt. We have this equation. And we know that dq divided by t actually is the I from chapter 1. So we can conclude that the capacitor relationship is I equals to C dv dt. I, the relationship between the I and dv dt is the slope. And then the slope will be the capacitance value. Some more, we also can express in the time domain. So by using V equals to Q divided by T at the instantaneous time. Instantaneous means at that time. At time at 1 second. At time at 2 seconds. At time at 3 seconds. We can express the voltage across the capacitor in this form. V equals to 1 over C from time t0 to a time, integrate the I dt plus V at the time of t0. We also can express the power delivery to the capacitor. As usual, P equals to VI. I have my V, my I. If you still remember, my I actually is C dV dt. So I put my C dV dt as I. Then I copy my V. So this is my power. I also can put it as an energy W. W equals to from negative time infinity to a certain time. Differentiate, integrate the power at a certain of the time. Then I can put it in a simple way, which is half CV squared. This is my energy stored in the capacitor. With this equation and that equation, those equations, I can put it into W equals to Q squared over 2C. No need to memorize. I will summarize it later. So the properties of capacitor: an open circuit to DC. Okay, capacitor will act as an open circuit. Open circuit means there's no current flowing through to the capacitor. When we connect the battery to a capacitor, it will open circuit, so no current flow. Right? Since the dV dt will become 0. So example, I want to calculate, let's calculate the charge stored on the 3 picofarad capacitor with a 20 volt across it. So we know that Q equals to CV. My Q, I want to find my charge, which is Q. My capacitance is a 3 picofarad, so 3 times 10 to the power minus 12. My V is 20 volt, so I have a 60 picocoulomb of charge. Then I need to find the energy stored in the capacitor. How to find it? I use W equals to half CV squared, which is equals to half times my capacitance is a 3 picofarad times voltage. So my voltage is 20 volts. Square it, I become 400. So I have a 600 picojoule on this instance. Okay? Another example. The voltage across the 5 microfarad capacitor is this voltage. The voltage which is variable. Variable. Cost function is variable. It can go to positive and then go to negative, then go to positive. It's variable with time. From time 1 it may be positive. From time 2 it becomes to negative. So what we need to do is, now we want to find the current. We use this equation, I equals to C dV dt. I know that my C is a fixed, 5 times 10 to the power minus 6, which is 5 microfarad. Then I put D dt. Then my Vt, my V is actually 10 cos 6000 T. So I differentiate my cost function with the time T. Then I find this one. Differentiate cost, I have a negative. So 5 times 10 to the power minus 6, I copy. 6000 is after I differentiate cost, I have a 6000 here. Then I times 10 because I have 10 here. Then when I differentiate cost, I will get sine. Then I have equals to blah blah blah, negative 0.3 sine 6000 T ampere. This is how we use I equals to C dV dt. So what about when we series or parallel capacitor? It is almost the same as the resistor. We can series, we can parallel the components. So when we talk about a series or parallel capacitor, we come to this circuit. We have a voltage source, constant voltage source, then we connect all the capacitors C1, C2, C3, Cn with the I1, I2, I3, In. Then actually we can put into an equivalent capacitance value. How we do that? First, we need to find some feeling on how to get the formula first. First, I know that my I go in will equals to I go out. Apply current, Kirchhoff current law, is it? KCL. So I, Kirchhoff current law. I go in become R or out at this node. So my I equals to I1 plus I2 plus I3 plus blah 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 become In. And then I know that my I equals to C dV dt. So I put I1 C1, I2 C2, I3 C3, In Cn. And I know that my dV dt are the same. So I summarize, I factorize my, how come I missed out this one? Oh, okay. So I summarize my, I factorize my dV dt and found that, oh, actually my C equivalent capacitance actually is a summation of my CK, which is C equivalent equals to C1 plus C2 plus dot 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 plus C3. So if in this case, when my capacitor connected in parallel, I can find my equivalent circuit whereby C1 plus C2 plus C3 plus until Cn. This is for parallel connected capacitor. So what about series connected? So a voltage connected the series capacitor C1 plus C2 connect to C3 connect to Cn. So I use voltage starting point. So my total voltage supply actually to equate to V1 plus V2 plus V3 plus Vn. So I know that my V equals to 1 over C blah. Then I put this one and then I factorize it and then I move some of it. Then I found that 1 over C equivalent actually equals to 1 over C1 plus 1 over C2 plus 1 over Cn to get this C equivalent. Or we can get the C equivalent by C1 times C2 times C3 until times Cn divided by C1 plus C2 plus C3 plus Cn. So let's have a look on the example. Now I want to find the total capacitance value across A and B. First, I need to see the farthest first. So I know that 5 microfarad and 20 microfarad are connected in series. So I use 20 times 5 divided by 20 plus 5. I have a 4 microfarad. And then this 4 microfarad, it is parallel with a 6 microfarad. And also parallel with a 20 microfarad. So I use 4 plus 6 plus 20 equals to 30 microfarad. And then this 30 microfarad actually connected series with a 60 microfarad. So I use 30 times 60 divided by 30 plus 60 become 20 microfarad. This is the equivalent circuit. So let's come to the inductors. This is the inductors. Typical form of inductor. Inductor consists of a coil of a conducting of wires, which means it is one wire only, but we coil it together. Then inside it has a cross-sectional area, what is the material we are using, and number of turns. Then we have the length as well. So, a passive two-terminal electrical component designed to store energy in its magnetic field. Application: electronic and power system. It used in electronic and power system. Same as well. The two-terminal electrical component used to store energy. Capacitor also store energy. Inductor also store energy. Okay, they are all both passive elements. The application is to be used in electronic, power system, power supply, transformer, radio, TV, radar, electric motors. A practical inductor is usually formed into a cylindrical coil. This is called cylindrical coil with many turns of conducting many turns. So just now we have a capacitor. We use a capacitance to measure its ability. Inductor, we use inductance to measure the ability. So inductance, what is that? L is the property whereby an inductor exhibits opposition to the change of the current flowing through it, measured in the Henrys. Which means, actually the inductor, it don't like people to change the current itself inside the coil. If initially there's no current in the coil, so when the current want to inject into the inductor, so it will say, hey, please don't come in into my inductor. This is the properties of inductor. Inductance is the property where an inductor exhibits opposition to the change of current, which means if the current constantly flowing, suddenly it reduced. This is a change. So the inductor don't dislike change. That's why it will oppose it. It will say, hey, don't change. Don't change. Then it will come out an equation where V equals to L di dt. See, di dt means the change of the current. So the inductance of an inductor depends on its physical dimension and construction. So just now we have a C equals to epsilon A divided by D, the distance, right? It is used to measure the capacitance value. Same as well in the inductor. We have N squared times mu times A divided by L. See, this one will be related to the geometry as well. N squared is the number of turns here. Mu is the permeability of the material for this one. A is the area here and L is the length here. So inductance can be increased by increasing the number of turns N, or using material with a higher permeability as a core, mu, or we increase the cross-sectional area A, or reduce the length. So mu depends on the material of the core. The core may be made of iron, steel, plastic, or air. So we have the inductance actually related to the material itself, also related to the geometry of the hardware. This is the inductors. Solenoid wound inductor is like this. Toroidal inductor is like this. We also have a chip inductor is like this, which is look like the resistor. And then the symbol become this. Or with iron core. Air core means there's air. Iron core means inside got iron. then variable with an arrow. So now we need to do some relationship again. So we have a V equals to L di dt. When we talk about engineering, always come with mathematics. So V equals to L di dt, and then when integrate it, so I get this equation, where I at the time is the total current for blah blah blah. Okay? From negative time to certain time, and I at a negative infinity here will be starting from 0. So what about power delivery to the inductor? So P equals to VI, and I know that my V equals to L di dt. So I copy only L di dt, L di dt, and then I copy I. And then I do some, what is that? Oh, I substitute. I also can copy I, which means I change I, become like this. We have two forms, but no worry. Let's have a look. What about the energy store? So we use this general equation, then we put all the P that we have, we can blah 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 become half Li squared. It is analogous, which is equivalent to the capacitor. Capacitor of the energy store is half Cv squared. Inductor is half Li squared. So assume that the energy is 0 at time initial time. The inductor energy will become half Li squared. So the properties of an inductor, it will act like a short circuit to the DC. When there's no change of the current inside the coil, it becomes short. Then the current just directly flow through. Okay. So example, the current through the 0.1 Henry inductor is like this. And then we need to find the voltage across the inductor and the energy stored in it. So we use V equals to di L di dt. L is 0.1 Henry given there. Then this is my I put my I here. So 0.1 times d, copy d over dt. Then I copy times t times exponential -5. I do some differentiation. If you still remember how to differentiate it, first I differentiate the time. Second, I differentiate the exponential. Okay, just mathematics. Then I found that the final value is like this. This is how it works. What about series and parallel inductor? Just now we talked about series and parallel capacitor. So series and parallel inductor, it is analogous to resistor. So if let's say L1, L2, Ln connected in the series, we have a V, right? The total voltage will be distributed to V1, V2, V3, and Vn. So I sum up together, and I know that my V equals to L di dt. I put it all together, then I summarize that, actually my L equivalent is equals to L1 plus L2 plus L3 until Ln. Same as well, if I connected the inductor in parallel, I also can put it as a equivalent inductance. It begins from the I. So total I go inside will become total I go outside. So I in will become I1 plus I2 plus I3 plus In. Then I use that one of the equation. Then I get all this, and then I can summarize that, actually my equivalent inductance can be found like this or like this, which is analogous to the series of the capacitance value. So let's have a try on the example. We want to find the equivalent inductance of the circuit. First, this is connected as series. So series is add up together. Series 7. Series is add up together. 20 plus 12 plus 10, it becomes 42. So I know that 7 Henry and 42 Henry are connected as a parallel. So I use 7 times 42 divided by 7 plus 42. I have a 6 Henry. So 4 Henry connected with a 6 Henry connected with a 8 Henry. It is actually a series. So I have a 4 plus 6 plus 8 become 18 Henry. This is a summary. For resistor, I have a V equals to IR. For capacitor, no need to memorize. For inductor, V equals to L didt. So relationship I to V. This one, I equals to VOR. Then my capacitor is I equals to C dV dt. No need to remember. No need to memorize, sorry. So P or W, we have a P equals to I square R or V square over R. W will be half CV square for capacitor. W will be equals to half Li square for inductor. When we want to find the equivalent circuit of the resistor, R equivalent will be R1 plus R2. Have a look on the inductor. L equivalent will be L1 plus L2. But C will be C1 times C2 divided by C1 plus C3. Parallel, R equivalent equals to R1 times R2 divided by R1 plus R2, which is the same, analogous to equivalent of the inductor. Then capacitance will be C1 plus C2. At the DC condition, it is the same, but when at the DC for capacitor, it will become open circuit. At the DC condition, inductor becomes short circuit. So thank you very much. Hope you enjoyed it.